Hi, I'm Steve Ward, and in this session I'm going to talk about PROFINET. So we'll cover an overview of what PROFINET is, we'll look at some details of the implementation, and we'll take a look at how we can do diagnostics in case something goes wrong with your network. So the history of PROFINET is that it's the development of Profibus over Ethernet. It's a very similar protocol to Profibus, but whereas Profibus uses a proprietary layer, although that was later standardized, PROFINET is standard Ethernet, although there are some caveats that I'll cover later. Now, PROFINET was originally called Process Field Net or Process Field Network, and it was standardized under two standards, IEC 61158 and IEC 61784. PROFINET these days is maintained by Profi International, or the PI organization, and as I mentioned, it's mostly standard Ethernet. You can certainly run PROFINET on purely standard Ethernet. Some functions do need specialized networking equipment, and again, I'll cover that a bit later. As of 2018, my belief is that PROFINET was #1 in industrial I/O markets and had 23% market share of the industrial Ethernet networks. Competing standards include Ethernet IP, which is probably the main other standard for normal use, and there are also some specialized motion networks for Ethernet, including EtherCAT and a few others. But for I/O, certainly for standard I/O devices, PROFINET, I would say, is probably the leading installed network that exists. Now, I've got a separate presentation and slide deck that covers Ethernet, so if you want to understand more about Ethernet, go and see one of those. The interesting thing about PROFINET is it's not a single protocol. So you've got Ethernet is the underlying network layer, which transfers the bits across the network and then is responsible for getting bits and bytes across the network. That also covers the actual physical media you use, such as fiber or copper and so on. On top of that, we then have several software protocols that we use, and together these make up the PROFINET network. So first of all, for non-critical data, i.e. things that don't need to be transmitted faster than about 100 milliseconds, so that can include alarms, for that we use TCP/IP. For peer-to-peer networking, we use CBA, and that has a cycle time of around about 50 to 100 milliseconds. There's then two protocols for PROFINET itself. One is called RT, or real time, and this is used for cyclical I/O data. And when you can configure your devices, you can select a cycle time of 1 to 512 milliseconds, going up using like a binary system. So there's 1, 2, 4, 8, 16, 32, and so on. You've also got isochronous real time, or IRT, and this is intended for drives and very high speed I/O, particularly servo motion, where you need cycle times which are less than 1 millisecond and also very low levels of jitter. You can imagine for motion, you've got rotating devices, the jitter needs to be very low so that the signals are received at the same time each cycle, not just that the cycle time is very low. So the jitter on IRT is less than 1 microsecond, so very low level jitter. Now, interesting with IRT, you need special Ethernet hardware in the controller to make sure that the data is sent on the right time, but you don't need it in the I/O device. So IRT is normally more specialized, but RT, CBA, TCP/IP, they can all use standard Ethernet. You've also got what's called a discovery protocol, or DCP, and that's used for configuration. And the idea of the discovery protocol, devices announce themselves on the network, the discovery protocol can see those devices and then allow you to configure them, and it can also be used for limited diagnostics. One of the things the DCP lets you do is flash the LEDs on the device. So if you're not sure which device you're working with, you can use the DCP to tell that device to flash its LEDs, and then you'll know which is the device you're configuring because of the flashing LEDs. If you configure it to flash and they're not flashing, you've got the wrong device. These are the key features and benefits of PROFINET. The first is it uses standard Ethernet. This means that you can use standard cables, including 100 megabit and 1 gigabit networks, standard RJ45 type connections, We've also got fibre. We can run under 100 meters using copper cable. We can go up to several kilometers, up to 80 kilometers using certain sorts of fibre. Typically it uses a full duplex switched network. And because it's standard Ethernet, that means it's well understood by the industry, and some of the protocols are well understood as well. And also it's compatible with tools like Wireshark and so on. Because it's Ethernet, you've got a wide choice of network architectures. For fault-tolerant rings, then there is an option there called Media Redundancy Protocol, and I'll cover that. Still standard Ethernet, but the thing there with standard Ethernet is if you create a ring, the packets are repeatedly sent around the network and the network would crash. MRP uses like a software switch to stop retransmitting the packets, and that allows you to have a fault-tolerant ring. If there's any single point of failure on the network, such as a cable or an I/O device, the packets are rerouted through the media redundancy controller, and that allows you to have fault tolerance and survive any single point of failure. Depending on your network as well, MRP can also survive multiple failures, but that would depend on exactly what you have in terms of your architecture. Now, PROFINET is open, it's supported by many vendors, tends to be more European. Certainly it was originally developed by Siemens, who are a European manufacturer, but many other vendors have now taken up PROFINET. And as it's an open protocol, it's now no longer that you have to go to Siemens for the chips. That was one of the issues in the very early days of PROFINET, but that quickly went away as other people came along and allowed you to implement the protocol using either their software stack on the standard Ethernet device, or you could buy dedicated chips from multiple vendors. So very open, is supported by multiple vendors. Some vendors support multiple Ethernet protocols anyway. Some people support Ethernet IP and PROFINET and others. Some people only support PROFINET as their I/O, but it has got wide support by many different vendors. And it's interoperable. In theory, a device from one vendor will work with a device from another vendor, and that usually works in practice as well, because the PI organization does have regular interoperability testing where people can turn up, put their devices or their controllers on the network, and they can test it with other people's devices to make sure it works. If a device doesn't work for some reason, then the vendors should work together to make it work, because it is intended to allow interoperability. And if they aren't working together, there could be a restriction on the implementation of the protocol. So that's one thing, particularly around redundancy. But otherwise, they are supposed to work with each other. And if one device isn't fully conforming to the protocol, the vendor should fix that so that it is fully interoperational with other devices. The challenge there, of course, is if you've got two vendors, it's making them agree that one of them is wrong. And that's why you might also want to get a third vendor involved. If you've got two devices that can talk and a third one that can't, likely then it's a problem with the third one. But again, that's where the interoperability testing is meant to come in. Now, the protocol itself supports simple name-based configuration. So there are IP addresses. You do need to do a bit of network configuration, but the protocol does support automatic assignment of IP addresses. But ultimately, each device has a name. So for example, you might have an I/O device. You could call that I/O device number 1, the second I/O device number 2, or you could use something meaningful, such as main machine I/O, secondary machine I/O, or whatever makes sense in your application. So name-based configuration, which makes it easier for humans to understand. Now, in order to do the configuration, there's what's called a GSDML file. So Profibus uses a GSD file. GSDML is an extension of that Profibus file using XML, hence the ML part. It is human readable to an extent, although I would argue that it's going to be very difficult to read. First of all, because of the size of some of the GSDML files. They can easily get up to 5 megabytes or bigger. Also, some of the tags which you use might not be obvious to humans. In theory, it is human readable, but the idea is the GSDML file allows your configuration software to understand what the capabilities of your I/O device are, and that includes all of the I/O modules that might be plugged into the I/O device, along with all their configuration capabilities. But what it means is, in order to interoperate an I/O device with a controller, the GSDML file comes from the vendor of the I/O device. You use that with the vendor who makes the controller's software. in order to configure the device, and then it should all work. The only restriction there is that some vendors don't update all of their GSDML files. Some vendors don't update their GSDML file support, so you occasionally get interoperability issues around different versions of GSDML file. But again, that should be fixed by the vendors. They should be using the latest version. And in some cases, it's possible to use older versions of GSDML file. It just means that you might not be able to use some of the more advanced features. Another aspect of PROFINET that's good is it does support redundancy. Depending which level of system redundancy and cable redundancy you use, you can have redundant controllers, hot standby PLCs, you can have redundant network cables, mainly using MRP, and you can have redundant I/O devices, and you can mix and match that redundancy so you can have very high levels of fault tolerance. So very good for redundant applications as well as simplex applications. Beware though, not every device supports redundancy. Some devices that are redundant might not work with other devices that aren't redundant, or it might be that they do work but only in simplex mode. So for example, you might have a hot standby CPU system with simplex I/O. If the I/O doesn't support redundancy, it can only be controlled by one of the master controllers. If that controller stops because it fails or is taken offline for maintenance, then the I/O is no longer controlled because it doesn't support redundancy. But it does allow you to mix and match and do quite a lot of interesting things without having to worry too much about what your final architecture is. Also, the Ethernet standard itself, that also supports multiple protocols. So it gives you a lot of different choices of architecture, including running non-PROFINET traffic on the same network. So for example, you might combine that with CCTV, voice over IP, different network protocols like Modbus TCP. They could all coexist on that same network. And what helps there is, on the Ethernet side, the main PROFINET standards include quality of service, so in theory they have a higher priority on the network. Of course, ultimately it's going to depend on your network bandwidth, so there's a degree of architectural support there that you might need to consider. But generally it does mean that you can just have a single Ethernet network and you can put all of your devices on it and there's no issues about them all working together. So these are the standard architectures. And these are not exclusive, you can mix and match, so you can have a combination of bus and star. It's also possible with the MRP network as well to combine multiple different types of device as well. But if we stick with the basics, the commonest architecture is a bus. And what we have here is we have a controller that is connected to the first I/O device. Many PROFINET I/O devices have a built-in network switch with 2 ports. So what that means is you can connect your controller to the first port. The second port can then be connected to the first port of the next I/O device. That I/O device can then have its second port connected to the next I/O device and so on. So what you can do is you can create like a daisy chain architecture with no additional hardware. So this is good because it reduces the amount of additional hardware you need, simplifies wiring, reduces panel space and so on. And the network is designed to do this. So you've got a very good architecture there with no additional hardware. Of course, there is a problem there. You have got single points of failure. If a I/O device that's in the middle or close to the controller fails, or if a cable is unplugged, then of course you do lose downstream connection, and that's where MRP comes in, and I'll come on to MRP in a minute. Now, another common architecture for Ethernet is like a star network. In this case, you have an Ethernet switch. You connect your controller to the Ethernet switch, and then the Ethernet switch is used to connect to your I/O devices. So this might be used for simple devices which don't have a built-in switch. It might also be used if you just want to have a connection of different speeds. For example, your controller might be on gigabit Ethernet and your I/O devices might be on 100 megabit, so your Ethernet switch can handle that. And it also might be that you're combining a bus and star architecture depending how many and what types of device you have. So with both a bus and a star architecture, there's a single point of failure. Of course, the controller is a single point of failure, and this is where system redundancy comes in, but we'll talk about that later. But the key point here is, if you had a failure in part of the network, such as with a bus structure, if there was an I/O device that's close to the controller, or one of those cables failed, you'd have a single point of failure. With the star network, it's a bit better, but you've still got an Ethernet switch that's a single point of failure. So this is where MRP, or Media Redundancy Protocol, comes in. What you do is, using the switches that are built into the controllers and the I/O devices, or possibly using a special MRP capable switch, what you do is you daisy chain from the first device to the next and so on, and then on the last device you use a single cable to go back to the network port on the controller, and you create a ring, hence the fault tolerant ring part. And this gives you redundancy on the cable. It's not really redundancy though, but you could argue, yes, you've added the extra cable, so it's sort of redundancy. But I would say it's more fault tolerant than redundant, but it achieves the same effect. If there's any single point of failure inside that fault tolerant ring, the system will carry on running. Because what happens is the controller sends data one way using its main port. That's transmitted by each I/O device to the next I/O device. And then on the network you have a media redundancy controller, or MRC, or a master, MOM rather. MRC is actually the client, so media redundancy master. What happens is the media redundancy master detects the returning packets, and when it receives them, it stops sending them back around the network. As I mentioned earlier, if you did a ring with normal Ethernet, there's nothing to stop the packets being transferred multiple times, and then that can cause a overload on the network within a few milliseconds because the packets just are sent and resent and resent. So the media redundancy manager, the MRM, makes sure they're not resent, so that gives you your fault tolerance. If the media redundancy manager detects that a device isn't sending packets, so that the send packet isn't received, then it will send packets in the opposite direction as well as the forward direction to make sure that as many I/O devices are available can still be contacted. So the media redundancy manager handles that, and also the media redundancy clients can have an action there because they can tell the MRM when they've returned to service, or they can even warn it of impending shutdown. The challenge with the fault tolerant ring is that it can only handle a single point of failure. If you get multiple points of failure, then it won't work. So for example, if the first and the last I/O device are both turned off for maintenance or both fail, any intervening I/O devices will not be able to receive any I/O, so they will go to their default states or turn off. But this is true of any system. It's very difficult to handle multiple types of failure at the same time. Also, we talk about it handling a single failure, but it could be you could get multiple failures and the system will still degrade gracefully. So for example, we've got 3 I/O devices here. If the first and second I/O devices fail, we've got 2 failures, but it will be fault tolerant to some extent because the third device will still continue to work. So in order to determine what the effects are, you do some sort of failure mode effect analysis to work out what happens, and then that can aid you in deciding what your network architecture should look like and how many devices you need and so on. Now, I've used the term I/O device. An I/O device in PROFINET is a device that is not a controller but has some sort of I/O connected to it. It's an industrial network. We're controlling a machine, so I is inputs, O is outputs, and the I/O device translates the physical inputs from the plant into the electrical and binary signals that the system uses, or maybe analog signals if it's an analog device. And on the output side, we take the output signals and convert those into something that can be used in the real world in the field. Now, the I/O device is defined by a GSDML file. So the GSDML file is provided by the I/O device vendor, and that's used in the controller's configuration software to actually configure the I/O device. Now, very small devices may be fixed, and there's a concept of a slot and subslot that we use, and it's possible for a small device to be completely fixed in terms of its architecture and its inputs and outputs and so on, and what it can support. But the idea is, by having multiple slots and multiple subslots, what we can do here is we can enable a modular I/O device, for example, an I/O device that might have configurable I/O modules. We can allow the GSDML file to be configured to handle that, so we can have configurable I/O devices rather than fixed I/O devices. Subslots also help there, because as well as having multiple slots, one for each I/O module, you can also have subslots. So that might give you options for configuration of the I/O module, such as different options, and also there might even be sub-modules within the I/O module itself. And what the GSDML file does, that defines what configuration you can perform for the I/O device, including what can go into those slots and what can go into the subslots. Now, when you configure the system, you have to configure each slot or subslot, and then in your controller, this is where you would allocate to the I/O map for the I/O device. So of course, input modules would typically map into your input data table, outputs would map into your output data table, and so on. And then there may be additional configuration if the I/O device or module allows. So for example, if you've got an I/O module, particularly on outputs, you might define what is the default state. Is it go on? Is it go off? Or is it hold last state? So that's a typical thing you might have in outputs. For analog modules, you may be able to configure the analog module or the analog channel itself. So voltage or current, 0 to 20 milliamps, 4 to 20 milliamps, RTD or thermocouple, and so on. Maybe even engineering, scaling, and so on. And all of this depends on the complexity of the I/O device. So this is where PROFINET is very flexible, gives you a lot of different options there if you're a vendor to allow you to configure an I/O device. However, most people try and keep it simple, and certainly we see this in some vendors who are more mechanically minded. For example, things like pneumatic type systems, they try and keep it very simple. But when you get up to more advanced devices, particularly in process control, then you can have a lot more flexible configuration options. And the great thing about PROFINET is it covers both of those. So here's a bit more detail on the media redundancy protocol. It is standardized under IEC 62439-2. As I mentioned, it can overcome any single failure, although you've got to be careful there. Just because something has failed doesn't mean your system will continue to operate. If you have an I/O device that's failed, if you've got critical I/O on that device, then it might be your machine can no longer function as it needs to. But where media redundancy protocol is really good is at handling single point cable failures. It's really good for that. It's less good for handling I/O device failures. And as I said, if you get multiple failures, well, then you might be in trouble as well, because depending on what's failed, you might find that multiple I/O devices are no longer communicating, and now you can't control the machine at all. Now, MRP operates at the MAC layer, so you need a 2-port switch in the I/O device. Most I/O devices do have a 2-port switch. It's a switch which is operating at low level at MAC layer, so there will be 2 MAC addresses, but there will only be 1 IP address. But again, from a configuration point of view, that's normally straightforward. You don't have to worry about that because the GSDML file handles that side of it. However, if you do look on the network, you will see those multiple MAC addresses. Now, another point is not every I/O device has those 2 ports. Some only have 1. If you want to do MRP with a device that's only got a single network port, then you would have to use an MRP switch, and then you would have an additional single point of failure of the switch and of the single cable that connects to your I/O device. But it is possible to integrate devices that don't support MRP onto a network that is using MRP. So again, you've got this nice flexible architecture that gives you quite a bit of control. Now on the ring, you've got one manager, media redundancy manager, and one or more clients called MRCs. Sorry, MRC is media redundancy client. Now all the nodes in the ring must support MRP. So as I said, that either means you need an I/O device that supports MRP using a switch, or you need a switch itself that supports MRP. It is possible to use a unmanaged switch and use that as part of your MRP network. I would argue if you did that, then your unmanaged switch isn't really part of the network, it's just acting as a piece of cable. So it's possible, but normally that doesn't make much sense in a practical network. You could do it if you wanted to extend the network. So for example, you might want to go on a copper cable network between 2 devices, and it might be more than 100 meters. So you could use a switch as like a repeater. But you are exposing the network to additional failures. And if that non-MRP switch did fail, then all you would notice is you've got the same effect as if that piece of cable had failed or was unplugged. So it's not strictly true that all nodes in the ring must support MRP, but it's good practice that they do all support MRP. Now what the MRP ring does, it's those ports, they support blocked unforwarding. The idea there is if you've got a blocked ring port, that drops all receive frames except MRP control frames, and a forwarding ring port, that forwards all receive frames. So the idea is, that ring port, that's how the system works. Think of it as like a switch. So if you look at the diagram over on the right here, you've got the controller MRM here, and it's in the blocked state. So messages travel out of the port on the left, go around the network using the daisy chaining, come back into the port on the right, and then they are blocked. They are not retransmitted by the controller. This is what we call, in this case, the ring is closed. So one media redundancy manager ring port is blocked and the other is forwarding. And then on the MRCs, all the ring ports are forwarding. So that's what we've got there on that top right diagram. In case of a failure, the ring goes to the open state. So when there's a failure of a link between two MRCs, both ring ports of the MRM are now forwarding. So instead of them being blocked, we now forward through both ports, going out in both directions. So as you can see here on this lower diagram on the right, what we've got here is we've had a cable break. In normal circumstances, if there wasn't MRP, then any device downstream of that first I/O device would no longer be able to receive network packets. But what happens is, because the controller is now forwarding, packets achieve direction and are sent in both directions, and that way we can achieve communications to all of the devices despite the loss of that cable. Okay. You'll also notice that the MRC as well, they go to the blocked state. And then this is the real aim of media redundancy protocol. In general, the cable is more likely to break than any other component. Electronic components are extremely reliable, but cables can break because of outside influence, such as vibration. Maybe a forklift drove into some column and took out some cables. Although I'd argue if that happens, maybe still running your control system isn't your main concern at that point. But there are lots of occasions where a cable might break, but you still want to run your network. So for cable issues, media redundancy protocol is really good. But it will also work if the I/O device itself fails. So if an I/O device fails, yes, you'll lose the I/O on the I/O device. But again, what you will do is you will find the I/O devices either side of the failed I/O device. They will go to the blocked state. The media redundancy manager will be in the forwarding state, and that will allow you to continue communications with all the remaining I/O devices. Where it becomes challenging is if you get multiple failures, and that will depend where the failures are. And again, this is where you can do your failure mode effect analysis to work out what happens under particular circumstances. Now the eagle-eyed here might point out that your controller is a single point of failure, and in this architecture, yes it is. A single controller could fail, and then you wouldn't have control of your I/O, that's true. So this is where we can combine media redundancy protocol with system redundancy, where we can have CPU redundancy, and I'll come on to that soon. Now I've mentioned network switches. If you're using PROFINET RT, you don't require special Ethernet switches. You can use any commercial or industrial managed or unmanaged network switch. And the only thing you have to have is that you need that capability to support MRP if you're using media redundancy protocol. But if you're not using media redundancy protocol, then any switch will work. And this is good because if you want to extend the distances or if you want to combine architectures, these switches mostly have a capability to support these different options. So you can combine that bus topology with the star topology and so on, and you can have quite a complex network architecture. And as long as you don't create a ring, then there's no problem. If you create a ring, then you need to think about using MRP. You might also consider using STP, scanning tree protocol, or spanning tree protocol, or RSTP, which is rapid spanning tree protocol. Just be careful, but if you're using a PROFINET network for I/O purposes, STP is probably far too slow because it's got a recovery time of seconds. RSTP, you're still looking at several milliseconds, so I would say even RSTP wouldn't be fast enough. So if you're worried about a failure on the device, then you need to arrange it to use MRP. But the good news is, if you're not using MRP, you don't have to use special switches. And again, many devices, many I/O devices have a built-in switch to allow daisy chaining, so you don't need any switches at all. You just go from one device to another like we had in the earlier slides. Now, if you're using PROFINET IRT, that uses IEEE 1588, which is a standard that includes low-level timing signals, and that's why you need a special controller, because it has to have the IEEE 1588 protocol built into it. You can also use low latency unmanaged switches on the network, but if you're going to use any other switch that's managed, it would need to also support the IEEE 1588 protocol. So a bit more complicated when you're using PROFINET IRT, but the use cases for IRT, they're not the same as PROFINET RT. That's normally for motion applications, and then you might have additional restrictions by the vendor. So that's maybe less of an issue, but just be aware of that if you are using PROFINET IRT. You might notice that some I/O devices are labelled as supporting IRT. Again, you only need the special protocol support in the controller, so an IRT I/O device can support both IRT and RT without any special extra configuration or any extra hardware. So if it's an IRT I/O device, you don't have to worry. It's really if the whole network is IRT, or if you want to use the IRT capability in the controller, that you need these special switches and the special controller support. Now, a lot of people ask, I can run PROFINET over cable. Yep, great, copper cable, works fine. I can run it over various types of fiber. Yep, no problem. These days, the latency of a switch is so low that there isn't a problem. It doesn't affect the time on the network. Certainly for PROFINET RT, if you're talking about a cycle time of a millisecond, the actual network transfer time is nanoseconds or most microseconds, which is order of magnitude faster than the actual cycle time. So any old switch will work, even if you have multiple switch hops, and even if you're doing conversion from copper to fiber and back again, not a problem. Some people say, well, okay, I want to use wireless. Does that work? Well, the short answer is yes. Wireless is supported. The only thing you need to be careful there is your wireless network fast enough to support the cycle time you need? Wireless is great. Modern networks can be very fast. I've got here, we've got IEEE 802.11 with 2.4 gigahertz, and 5 gigahertz has been added. We now have 6 gigahertz. So if you're using a high enough speed network, then you'll have no trouble. It will work. But if you're using one of the older 2.4G standards, you might find it's not fast enough to be able to achieve the cycle times you want. So the network will still work. Performance will be affected though, and you might need to reduce your cycle times. We also support Bluetooth, IEEE 802.15.1, that's the Bluetooth standard. PROFINET will run over Bluetooth. Would you want to? I'd say no. You'd have a very short distance, and why? But if you really wanted to, you can run PROFINET over Bluetooth. A key point though, PROFINET is not routable, but the protocols we're using, although the TCP/IP part can be routed, the actual PROFINET I/O protocol itself, the RT and the IRT protocols, they can't be routed. So everything has to be on the same network in terms of your IP network type configuration, and you can't route across another network. So routers and gateways would not work. Anything where you need a gateway IP address and your IP addresses are on different networks, that's not going to work. You could use some sort of tunneling software or tunneling device. Even a VPN, that should work, but you might run into problems with performance and routing and so on, and the actual underlying protocol might not work. So I would say if you're using PROFINET, everything really needs to be on the same network. It might be a very big network, but it's all got to be on the same sort of physical network. And as before, if you're using MRP, your switch needs to support MRP, and it will actually act as like an I/O device. But the MRP switch support, that makes sure that everything works properly. Otherwise, you can get into issues that you can't easily diagnose where the failure is. So for example, if you're using a switch as an extender on a cable, then that will work. But if the cable fails or the switch fails, okay, but now you've got a long length of devices to look at to work out where your failure is. So you might have several cables which might have failed and several switches on a very long run, and you won't necessarily know where it is. So better to use MRP and maybe even a managed switch with SNMP, the Simple Network Management Protocol, and that will give you better diagnostics to understand which device has failed, and that will allow you to recover more quickly. Now, I haven't covered redundant systems yet, but if you've got a switch in a redundant system, then ideally it needs to support both MRP and the system redundancy, and act as an I/O device, again for those diagnostics, but also it needs to support the system redundancy. And this means that also if you've got that switch device, it will have a GSDML file, and it will also need to be configured inside the controller. But that's important for being able to correctly configure your network and correctly supporting system redundancy. And I mentioned SNMP. SNMP is supported in most managed switches. I can't think of a managed switch which wouldn't support SNMP, but SNMP is great for network monitoring and diagnostics, using an SNP client to understand what device is working and what's failed. Anyway, generally PROFINET is very straightforward, and you normally don't need to worry about switches because the switch is built into the I/O device itself. So for many networks, it doesn't really matter about switches, but certainly you can switch the network if you want to. One reason for switching the network might also be to overcome issues around speeds. Some devices are 1 gigabit, some devices 100 megabit. One thing to note there is if you directly connect a 1 gigabit device to a 100 megabit device, there's a good chance it's not going to work, because one thing about PROFINET is the speeds are fixed rather than they will negotiate. So if you've got a gigabit device on a network with a 100 megabit device, one will be running at a gigabit and one will be running at 100 megabit. They won't change speeds to match each other, so you won't achieve communications. So that's one reason to use a switch. The switch can convert from a gigabit to a megabit, 100 megabits and so on, and vice versa. Otherwise, the simple answer is just make sure every device on the network is running at 100 megabits rather than trying to use gigabit networks. There's other reasons for not using gigabit as well, particularly in redundant systems, because the recovery time is actually longer with a faster network. So my advice there is, avoid switches, and if you're worried about different speeds, you can overcome that just by configuring everything at 100 megabit. So the only reason really to use a switch is for particular architectures like a star network, or maybe if you want to extend the cable distance. Another way of extending the cable distance, of course, is to use a fiber to copper converter, and then that will be transparent to your network. But again, remember that the more devices you add, the more potentially you're making it difficult to find and diagnose problems on the network. So the underlying PROFINET protocol is designed to establish connections between the so-called controller, which is typically your PLC, CPU, or whatever your controlling device is, and the I/O device. So the I/O device, of course, that's the device that's connecting your physical I/O in the plant to your actual controller over the network. So I is inputs, O is outputs. Now, the way the connection process works is, first of all, the I/O device is identified by a name, and this is initially set either by the vendor, and you might have a name that can't be configured, but usually what you use is you use that Discovery Configuration Protocol, DCP, along with a vendor provided configuration tool, and that DCP protocol and that tool, that allows you to set the name. It's very rare to have a default name. It might happen in some cases, again, depending on who your vendor is, but usually you want to be able to change the name because there might be multiple devices and you might want to give it a meaningful name. The other point about that name is it has to be unique on the network. You can't have two devices with the same name. Anyway, your I/O device is identified by name, and the name actually uses the UDP channel, so that's User Datagram Protocol, rather than the TCP, which is the Transmission Control Protocol. So UDP is used to transfer the name, and that's done using a configuration data, and there's a record data communications or connections relationship. You also have an IP address, so the IP address is also assigned, again using that configuration data, using a record data communication relationship. So if you look at the diagram here, you'll see that's the one in green at the top. The controller sends the data to the I/O device, and that data configures the I/O device. So this is where your GSDML file comes in, and this is where you tell the I/O device what modules it has and what the configuration for each module and potentially each channel in that module actually does. That's set at startup, or possibly whenever the system is initialized. Possibly, for example, it might be when you stop your PLC and go to run mode. Every time you go to run mode, that record data communication relationship is sent again. Now, once the I/O device receives its configuration, then you have an I/O data communication relationship. So the I/O data is for your cyclical process data. So these are all the inputs and outputs which are sent on a common basis. So typically a multiple of 2, so you're starting with 1, of course, 1, 2, 4, 8, 16 and so on milliseconds. A typical data transfer rate, it's going to depend on your application, but I would say it's rare to be faster than 32 milliseconds. You can go down to 1 millisecond for very fast applications, but in a typical application that might be 64 or even 128 milliseconds. Yeah, you've got to consider how long is your device going to take to operate, and if it's typical electromechanical devices and the machine isn't too fast, yeah, 64 milliseconds is probably about okay. 128 might be a bit slow, but it depends on the process. 32 again, fine. But if you're going faster than 32, then you've got to look at your PLC scan time to see how fast that is. And you don't want the I/O data to be much faster than the PLC scan, otherwise you're just sending more data than you need to. So the I/O data, that's your communication relationship for your cyclical process data, and that's sent on a regular basis. So that uses a dedicated real-time channel, and this is using that either RT or IRT type protocol, which is the specific protocol used by PROFINET. Now there is a record data communication relationship as well. This is optional, and not every device implements this, but the idea of the record data, that can be used in reverse direction from the I/O device to the controller for data logging. Not often used, but it is there. And then there's also an alarm communication relationship. This is sent, it's a real-time channel, but it's sent on an ad hoc basis when required. Yeah, hopefully there aren't any alarms, but when there are alarms, they are sent from the I/O device to the controller using that alarm communication relationships. Now all of those together, the record data CR, the I/O data CR, the configuration data, the alarm CR, yeah, they make up the overall application relationship between the controller and the device. Now all of those are required, and that makes up your I/O application relationship. If the I/O device fails or is turned off, or if your network fails, the I/O application relationship has to be re-established every time. So that application relationship is very important from a system point of view to make sure that each device knows what it is and who it's talking to. And if there's any break in the communications, as I say, that application relationship stops and has to be re-established to make sure that everything is configured and working. Now, data transfer happens on a cyclical basis, at least for the data. It's acyclic for the alarms. And then once data transfer is running, as I mentioned earlier, we are using the quality of service part of Ethernet to ensure high priority on the network. So in principle, your I/O data should have a higher priority than anything else on the network to ensure that it is sent at the correct time. But again, it is still possible for a network to be overloaded. But in principle, your PROFINET data has priority on the network. And then the AR itself, the application relationship, that continues until either it's terminated. For example, it might be if the controller's turned to stop mode, or if either end fails to see 3 cyclic transfers. So after 3 cycles of no data, and remember the data is configured at 1, 2, 4, 8 or 16 milliseconds or so, so we know what to look for there. If there are 3 failures to transfer data, then the controller will recognize the I/O device as missing, and the I/O device, if it's still working, will recognize that there's no control data, and it will go to its configured output states, either all on, all off, hold last states, or default states, or whatever is configured according to the I/O device. Now this sounds complicated, but this is all handled by the system. It's great to understand what's going on inside, but from a typical engineer's point of view, the only thing you need to worry about is setting the I/O device name and IP address using DCP, and then once the system is up and running, all of the data transfers happen automatically, controlled by the controller and the I/O device, and you see the data and the outputs get energized according to the controller outputs. So it's more complicated to explain than it is to use. Again, PROFINET, very straightforward to use, and we've got the earlier slide details the actual protocols used. But again, that's probably more complicated than it needs to be as well. All you need to know is, from an operational point of view, is the controller sends data to the I/O for the outputs and for the configuration. The I/O device sends data to the controller for, again, for the inputs and for any alarms that might occur. Now we can use BD redundancy protocol to create a fault-tolerant network. But what happens if the controller fails? This is where PROFINET system redundancy comes in. So PROFINET system redundancy is a way of eliminating downtime due to a single failure. And what we have is we have multiple types of redundancy, but the one that's commonest and easiest to implement is PROFINET version 2.3 type S2 system redundancy. And this allows you for controller redundancy. So you have two controllers operating typically in the hot standby mode. Those controllers would be synchronized using some separate synchronization mechanism. We're not synchronizing over the PROFINET network, we would synchronize using an external network. So depending on what PLC you're using, they would have their own dedicated Ethernet cable, or it might be a fiber cable, or they might even be unsynchronized and just you assume that the outputs are synchronized because the inputs are the same, because they're coming from the same input module. So this allows you to have the hot standby controllers. You use MRP for the fault tolerant network, and if you need redundant I/O devices, you just duplicate those I/O devices and do some sort of voting in the application logic for the I/O redundancy. And if you do all of this, you can create a redundant system where any single failure will not cause a stop of the system. And it's not just about failures, of course, it's also about maintenance. You might want to take a CPU down to update the firmware. Maybe you need to update the firmware in an I/O device. So by duplicating every single thing and using MRP, any single device can be turned off, any single cable can be unplugged, and the system will carry on operating. Now there is another level of PROFINET redundancy, which is PROFINET R2 system redundancy, and this uses two sets of cables. Now some people argue that this gives you more reliability. I disagree, because at this point here with S2 system redundancy, we can survive any single failure. Now what happens with the R2 system redundancy is you've now got dual cables going to each I/O device. So you could argue that that survives more different failures, because if a single cable is unplugged, then it will allow it to carry on. But we've already got MRP, so having that extra cable doesn't help because we've already got a fault tolerant ring. Now some people will do an analysis and say, well, R2 gives you an extra capability if an I/O device fails. And that is true if you've got simplex I/O. However, remember now that with R2 redundancy, you've now got an additional or more complicated I/O connection. So potentially your I/O is now less reliable because you've got more complexity at the I/O level. If you want to eliminate that I/O issue, then you would implement duplicated I/O devices. Now the other thing about R2 is it does potentially survive multiple failures in a better way than S2 system redundancy does. But this is where your failure mode effect analysis comes in. As soon as we get to a second failure, what is the second failure? So for example, you might have two power supplies operating the system in redundant mode. If your first failure is the first power supply fails, you can survive that because you've got a second power supply. If your second failure is the second power supply goes down, then the whole system goes down. Same as if you lose two CPUs or you lose two duplicated I/O devices. So it's much harder to eliminate downtime due to dual failures than it is to a single failure, because you don't know what that second failure will be. Now statistically, it's easy to calculate the downtime using mean time between failures for a single failure. Some things, of course, you can't calculate. You can't calculate if a cable is going to fail, because a cable either lasts forever, or maybe it fails but you don't know why, or it is damaged because of some external influence. Like I say, a forklift truck driving into a cable tray, that will damage that cable, probably damage a lot of other cables as well. But so it's very difficult to determine how often a forklift truck driver drives into a cable tray. That's impossible to determine. What we can do is determine the electronic failure rate. But even then, how does that affect a single failure, and then how does that tie into the second failure? you don't know when the second failure will occur. So statistically, we can really only calculate downtime due to a single failure. So I would say PROFINET system redundancy using S2 system redundancy with an MRP fault-tolerant network, and if necessary, duplicated I/O devices. That will give you the fault tolerance you need. You don't need to go to R2 system redundancy. Now, there are more advanced topologies you can create using PROFINET switches. So for example, you have a combination of duplicated and simplex I/O devices. Some are using MRP, some aren't. You might be transferring multiple network protocols over PROFINET using a PROFINET switch to say Modbus, TCP and so on. So yeah, multiple options there. But again, if you want a properly fault-tolerant system, you should probably try and keep it simple. Now, a key point with PROFINET system redundancy is S2 system redundancy and R2 system redundancy are not implemented by every device. It's still possible to use a simplex device on a controller redundancy system, but what will happen is the I/O device will only be controlled by one controller. So if you've got hot standby PLCs and your I/O is controlled by the master CPU, if it's a simplex I/O device without S2 system redundancy support, if that master PLC is turned off or fails, then the system will switch to your secondary or your backup PLC, but the I/O device won't, because it can only have a single application relationship. That application relationship fails, and then the I/O device stops being controlled and will go to its default state or on or off or whatever it is. So with S2 system redundancy, there is a slightly modified connection process compared to the previous slide. What happens is the redundant controller establishes an application relationship to the I/O device, and so does the backup device. So there are two application relationships. And what the I/O device does, it has a primary application relationship, which it uses to transfer I/O and alarms to the I/O device and the primary controller. And then you have one, or possibly more, but normally I've only ever seen it as one. Then you have a backup AR. These are connected, but do not transfer I/O or alarms. The I/O device only recognizes one primary AR at a time. And if that primary AR fails, then the secondary AR or the backup AR takes over. And it's up to the controller to tell the I/O device which AR is primary. And there is a concept of whichever one is the last one to tell the system which to use is the one that wins. So the I/O devices don't need much intelligence. And this, again, this is one of the aims of PROFINET. PROFINET is designed to be implemented on low-cost embedded systems, which is what your typical I/O system might be. So a lot of the control is down to the actual controller itself, which is assumed to be more intelligent. But anyway, type S2 system redundancy, that can allow you to eliminate downtime due to a single failure. The connection process is slightly more complicated, but again, provided your devices can handle that S2 system redundancy, it's pretty much transparent to the operation of the system. There are a few extra things you might need to consider for PROFINET system redundancy. In practice, I've never touched these because I haven't had to, but on a complicated network and to ensure the fastest performance, then there are a few things you can tune to ensure that the failover time is as fast as possible. So the first aspect is called maximum takeover time. This is the maximum time that the controller will wait for completion of an I/O failure from the primary AR until it receives confirmation of the new primary AR from the I/O device. MTOT, as it's called, maximum takeover time, this is monitored by the controller, and typically it's 6 times the longest I/O cycle time, plus 2 times the network transit time, which is often very short, plus whatever the MSOT is. So the MSOT is a different characteristic. This is the maximum switchover time, and that's defined for the I/O device. So you can't configure the MSOT. The I/O device itself has that pretty much hard encoded, but you can control the MTOT. There's another option here called the redundancy data hold time, or RDHT. This is the time interval during an I/O failover during which the I/O device holds outputs at their current values. Now the reason we have this, it could be several milliseconds between a primary controller failing or the primary network failing and the backup controller or the backup network taking over. So during that time, what happens is the IO holds data at its last state, but you don't want it to hold the data at last state too long, because if both controllers had failed, then we want the IO to actually switch off or go to some other default state. So hold last state, this is the redundancy data hold time. This is monitored at the IO device, and the redundancy data hold time, it starts when the IO device detects a loss of the primary AR, and it stops when the IO device recognizes a new primary AR. And this can often be configured so you can calculate what the redundancy data hold time should be, and then it's like a timeout. You can actually configure that the IO will then stop operating if the redundancy data hold time is exceeded by more than a certain amount. So the behavior in PROFINET system redundancy is that there are two controllers, typically with hot standby, and the idea is you've got the one controller would fail over in the event of a critical controller failure. That can include being powered off, in which case, of course, the controller's got no choice. Some controllers might have enough capacitance to be able to continue for a few scans for a graceful failover, which is often the case. It might also be if the controller is turned to the stop mode by the operator, or it might be if the controller experiences some catastrophic fault. For example, maybe there's a memory fault, maybe there's some sort of subsystem fault that causes the controller to stop. But the idea is, under normal circumstances, you've got a master controller with a backup, and it fails over from the master to the backup in the event of this critical failure. Now, controllers do not fail over if the active unit loses connectivity to an IO device. There's no automatic roll switch. In that case, what you're looking at is you're looking at the IO device's outputs. They will default after the redundancy data hold time. And what can happen there is then the application can use Diagnostics to assess the IO device communications module status, and then the application then can decide to command a roll switch. So this is one thing that you might need to consider in your application about the failover to the active unit if you lose connectivity to an IO device. This is something that's under the user or the application control rather than under the vendor control. Now there's another thing, if you've got two devices and they've got a redundancy link between them, so this is the two controllers with their separate redundancy link, it could be that after the last redundancy link fails, then you've got a potential situation where you could have a primary unit and a backup unit both trying to control the IO. So in this case, this happens because the backup unit can't determine the health of the master unit, so the backup tries to take over. And in this case, what should happen is the formerly active unit should detect an IO switcher over, and it should go to stop mode and relinquish controlling communications. Now, in some system redundancy applications, this is automatically handled by the CPUs. In some cases, you may need to do this in the application logic. So you need to consult your vendor's documentation as to how that should work and how you need to consider that. So moving on, let's cover PROFINET certification. The idea of PROFINET is it is standardized by PI, which is the PROFINET or Profibus Institute, and they handle the actual network protocol itself. And in theory, field devices must be certified by the PROFINET organization. Now in practice, not every device is certified. Some people just can't be bothered, or maybe they're only using PROFINET for their own communications and there doesn't need to be any interoperability. But in general, to have the PROFINET name applied to a device, it needs to be certified. So this means that the developer, they would develop a device and create the GSDML file. And then what they need to do is they need a vendor ID from the PROFINET Institute. Once they've got the vendor ID and they've configured the GSDML file, they will register for this certification test at a test laboratory certified for PROFINET. So there are PROFINET independent test labs. You go to one of those, and then the vendor tests that their PROFINET device is interoperable. There are basic hardware tests such as auto crossover and auto negotiation of the network, typically for half duplex and full duplex and so on. The PROFINET testing lab certifies startup behavior, that power up is error-free. They look at address assignment. There would be reading and testing of the GSDML file. Then there would be testing of the controller, downloading of the GSDML configuration from the controller to the I/O device. There would be I/O device tests with and without an I/O supervisor, possibly with two controllers as well, to make sure that the application relationship arrangement works. There would be interoperability tests and interaction with different available I/O devices. There might also be testing of diagnostics and alarms and standardized faults, such as network off-or-on or device removal and insertion. There might also be load tests and EMC tests. After testing, the vendor receives a test report, and if all of that is positive, then the manufacturer can apply to PI for a certificate, and when they have that certificate, they can use the PROFINET brand and label on their device. And then in most cases, it also means that because of all the testing that's done, that PROFINET device will interoperate with other PROFINET devices from other vendors. Now, it sounds like quite a process. Yes, it is. It is something that the vendor needs to manage, but it's not hugely onerous. And in order to guarantee interoperability, this is like a best practice to make sure that these devices can talk to each other. So here's the process for PROFINET configuration. I'm talking here about the complete configuration process, including designing the network. That would normally be your first step. So this is understanding what your application needs to do. You need to know how many controllers and I/O devices there are, and based on that you define your networks. Understanding what the application does, so you can define your update rate. Again, your update rate is typically 1, 2, 4, 8, 16, 32, 64 and so on. I would recommend, if you're not sure, a default update rate would probably be 64 milliseconds or maybe 32 milliseconds. The faster you go and the more devices you have, you may find you come across issues where controllers can't cope with that update rate. Another point is, if you're updating too quickly, for example, if you're updating much faster than the PLC scan, then you're just wasting network bandwidth. So you don't want to update too fast. Equally, you don't want to update too slow because you might miss signals on the actual field I/O itself. You then define MRP settings. Are you using MRP? And if you are using MRP, what's going to be the media redundancy manager? What are going to be the media redundancy clients? Normally that's a pretty straightforward choice because most I/O devices can only be media redundancy clients, and normally it's only the PLC CPU or the controller of the device that can be the media redundancy manager. Note that in a redundant system, you still only have one MRM. So you might have two controllers or two CPUs. In this case, people say, well, what happens if the second MRM fails? Well, remember, the idea of the PROFINET system is, in redundancy, we only survive the first failure, and that includes failure of the first MRM. If the first MRM fails, then the MRCs will assume the blocked or the forwarding position, and then they will still be able to communicate. And then the failure of a subsequent device is undefined because we're really only trapping the first device failure. Once you've configured your network and the overall architecture and the high-level settings, you would then import your GSDML files into the configuration tool, and then you would configure the slots and subslots. So what are the I/O modules in each I/O device? What is the analog configuration and so on? Then what you can do is you can assemble all your hardware devices and cables, and you can start downloading that configuration into the controller and performing testing. One thing you need to be careful of is you're using MRP. MRP isn't initially configured, so if you do connect a ring before you've downloaded, the network could possibly fail. So I would say, using MRP, do not connect the final network link until everything is configured. Once it's configured, then MRP will operate. But before then, you could accidentally create a ring that will stop communication and prevent you from being able to perform any configuration or diagnostics. So you download the configuration into the controller. At that stage, you will connect the DCP tool to the I/O network, and that's where you will assign names and TCP IP addresses to the I/O devices. Once you've done that, they will now be aware of their MRP configuration, and at that point you can connect the final network link if you are using MRP. And after that, you can then start testing the application. Make sure the I/O works. Use your whatever diagnostics are available from the vendor, or using SLMP or whatever, and then you can monitor and control the network. And you can use the PLC controller diagnostics, And you can also use the DCP as well as a low-level diagnostic to see that devices are all connected on the network. Now, the GSDML file is defined by the PROFINET organization, and as we mentioned earlier, it's an extension of the GSD format, which was used for Profibus, and it's in XML format, which is where we've added the ML to the file name. But effectively, the PROFINET GSDML file, it's a general station description file, so that's also where GSD comes from, general station description file, and it describes an I/O device. It's provided by the device vendor. If you don't have the GSDML file, then you need to go to the vendor of that device and get the latest version of that GSDML. Also, depending on what firmware version of module you've got, you may need to get an updated GSDML file to take advantage of the latest firmware capabilities. There's quite a bit of backwards compatibility with GSDMLs and devices, but of course if you've got a new feature, then it will need to be implemented in the GSDML file. Otherwise you won't be able to configure it, and then it probably will be switched off by default and you won't be able to use it. Now you can look inside the GSDML file. It is human readable, but not really, because first of all they can be very, very large. You know, a GSDML file of up to 5 megabytes is not impossible. The GSDML file does include a picture of the device as well, which is used as for snapshots and in the engineering tool. So sometimes a large part of that GSDML file configuration can be the picture. You know, it might be a bitmap which is uncompressed, and you might find your 5 megabyte GSDML file, 4.5 megabytes of that might be the picture. So if you really wanted to, you could remove that picture to reduce the size of the file. And what vendors do, they often compress those GSDML files so they take up less space on the device. So inside the GSDML file, you've got that picture I mentioned, which is optional, but then you've got lots of other details. You've got the GSDML file version. So typically that might be something like 2.3 or 2.4. Yeah, they're very recent versions. There'll be the profile identification. There will be a vendor identification. That's that vendor identification number that comes from the PI. There will be specific device identification. There would be all the configuration information. There would be details of any parameters that can be configured at the I/O device level. There would be details of all of the I/O modules and the slots and sub-slots that the device can support. There would be details of diagnostics and alarms that the device can support. So for a complex device, this is why you can imagine that GSDML file can be quite large. Again, a lot of the GSDML file is transparent to you as a user. What really makes the important aspect of PROFINET is the GSDML file is used by all of the vendors to describe what the I/O device can do. And a typical vendor on the controller side, they would have a nice graphical user interface which interprets what's inside the GSDML file and allows you to configure the I/O device on that basis. So there might be a combination of things like pull-down menus, simple selections. Rarely do you have to enter any raw values. The whole idea of PROFINET is to make things easier to use. So part of that is the GSDML file. That hides a lot of the I/O device complexity inside a vendor supplied file. The important thing is, wherever possible, make sure you've got the latest GSDML file and make sure you've got the correct GSDML file. I've seen some vendors who get a bit confused and they'll send you the wrong GSDML file. If things don't work, that's one thing to check alongside all of your standard configuration and diagnostics, like is the device actually there, what do the LEDs say, and so on. Make sure you've got the right GSDML file, because if that doesn't match the device will just not work. Now there is minimal configuration for MRP. One thing you've got to decide is which device is going to be your media redundancy manager or your MRM. Typically that's easy because it has to be one of the PLC CPUs or controllers, and if you've only got one PLC CPU, then it's automatically that device. It's rare for an I/O device to be a media redundancy manager, although it is possible, but in my experience most I/O devices can only be MRCs. Note that if you can't configure an MRM or an MRC, then it's possible the I/O device doesn't support MRP at all, in which case you would have to connect it on a non-MRP network. Now the configuration needed is that in order to ensure successful ring recovery, test packets are sent at a particular time. So if you're using a 16 millisecond update rate or above, then you've really got to make sure that you've got a configured test packet interval, a test packet count, and also the IO update rate. They need to be configured to match. So what you need to do is you need to configure that test packet interval and the test packet count, and they need to be less than the IO update rate times 2. Now this normally isn't a problem on slower networks, but where you've got an update rate of 16 milliseconds or faster, this is where you need to make sure that this is correct. And the issue here is the minimum test packet interval is 10 milliseconds, your minimum test packet count is 2, so you need to make sure that you time all of that correctly, because remember the application relationship is using 3 missed IO packets to trigger a loss of IO device. So you've also got additional test packets which are used by the media redundancy manager to detect a ring break, and you can use this diagram here to work out how to configure those to make sure that the ring break isn't detected when there actually isn't a ring break. So relatively straightforward. Do that calculation and the vendor will provide advice on how to configure that as well. Again, if you're using slower IO update rates, then it's not normally a problem because those test packets are sent quite quickly. So it only becomes an issue if your IO update is 16 milliseconds or faster. So finally, the thing to bear in mind with PROFINET is that there are potentially multiple scans in your application, and all of these scans are acyclic. That means they're not necessarily synchronized with each other, they're all operating independently. So you might configure a PROFINET IO scan of say 16 milliseconds, but that doesn't necessarily mean that your IO is going to update every 16 milliseconds. So you have to consider your PLC CPU sweep. If your CPU and your PROFINET controller are separate devices, which often they will be, even if they're in the same device, it's often a separate communications subset of either the operating system or of the hardware even if they're in the same box. So you've got the PLC CPU sweep with the backplane scan, even if it's an internal scan. You've then got the PROFINET IO production cycle. So this is where the PROFINET controller sends data to the IO. And what will typically happen there is the PROFINET controller is sending data to what's called the PROFINET scanner, which is the IO device's PROFINET connection. And then if you've got a PROFINET device, it may well have its own backplane scan, which is independent of all of these other scans. And if you've got 2 or more PROFINET IO devices, their scan times might be different. You don't have to have the same scan time on the network for every device. You might have one high-speed device running at 16 milliseconds, another device that might be running at 32 milliseconds or 64 milliseconds, and then all of the devices as well have their own scans. So you need to take this into account if you are particularly concerned with your response time, and there are calculations you can perform. You can add up potentially the worst case of your PROFINET scan time, your PROFINET network time, and your PLC CPU time. And the worst case is normally each of those scan times added to each other and multiplied by 2. That would be your worst case. Your typical case is that you hit all of the scans at exactly the right time and everything happens very quickly, within a millisecond or less. So that means your typical scan time is the average of those two. So your typical scan time is actually the sum of the PLC CPU sweep, the PROFINET IO production cycle, and the PROFINET scanner device. Normally the PROFINET scanner device to the IO is pretty quick, so we normally ignore that. So then it's just a combination of your PLC CPU sweep plus your PROFINET scan time is your typical response time for one-way communication. And that's where it starts getting complicated. If you want to do the input to output response time, then the input changes state. That's sent by the PROFINET scanner to the PROFINET controller. The PROFINET controller then sends it to the CPU. The CPU then has its own sweep time, and that might vary as well depending on what logic you've got, because it's not guaranteed that everything will happen in a single sweep. The CPU then writes an output back to the PROFINET controller. The PROFINET controller writes back to the PROFINET scanner, which again might be a separate device running on a separate scan time on a different device depending where your inputs and outputs are arranged. You've then got your PROFINET device, And what you also need to add on to this as well then is, what are your input and output responses? Now, in the vast majority of applications, this is not a problem. Your devices are generally much faster than your physical system can operate, but it can be an issue where you've got a very high speed machine. So this is where you might be running cycle times down at 1 millisecond. On the PROFINET network, of course, you'd have very fast I/O devices. You'd have a high-speed CPU scan, maybe using interrupts as well to improve the CPU response time. But you can calculate it all, but just be aware that you have got these multiple scan models and scan times, and they're all acyclic. So you can calculate the best case, the worst case, and the typical is sort of in between the two. And then based on this, it's also possible to optimize, because you can reduce specific scan times in each device as required. But just remember, you can only get down to a minimum. Beyond that, you're defined by the hardware. So for example, the minimum PROFINET I/O scan is 1 millisecond. So your absolute best response time is going to be 1 millisecond into the input, maybe 1 millisecond in the PLC, 1 millisecond back to the output. So you're probably looking at a fastest response time in the order of 3 milliseconds, but that might be a lot slower depending on how quickly your I/O and everything else operates. But again, for a particular electromechanical device, not a problem. You know, a relay or a contactor could take between 20 and 50 milliseconds to operate. So generally, as long as your control system is faster than the electromechanical part, then there's no problems.